Breaking news today, March 8th, 2026. Roughly 18 months ago, in the summer of 2024, researchers monitoring a remote stretch of Siberian tundra recorded something that had no place in their models. The ground was releasing methane, not in trace amounts, not from isolated vents, but in sustained, measurable plumes, rising from permafrost zones that had been frozen and chemically stable for thousands of years. More water was entering the basin. Temperatures had not spiked unusually that week. And yet the ground beneath the Arctic was exhaling a substance that scientists had long feared but never expected to see this way, this fast, this widely. Permafrost is not simply frozen ground. It is a geological archive. Across roughly 23 million square kilometers, nearly a quarter of the northern hemisphere's land surface, permafrost locks away carbon accumulated over tens of thousands of years. Dead plant matter, ancient organic material, microbial remains, none of it decomposed, all of it preserved in chemical suspension by temperatures that never rose above freezing. The National Snow and Ice Data Center estimated that Arctic permafrost holds 1.5 trillion metric tons of organic carbon, nearly double the amount currently in Earth's entire atmosphere. For millennia, this system was a carbon vault, stable, silent, self-sealing. In the summer of 2024, that number began to feel less like a statistic and more like a countdown. The Arctic has been warming at roughly 4 times the global average rate since the 1980s. What changed in 2024 was not the rate itself, but a cumulative effect reaching a physical threshold. In key regions of western Siberia, northern Alaska, and the Canadian subarctic, mean annual ground temperatures crossed 0 degrees Celsius and stayed there through winter months that would historically have refrozen the active layer. The freezing cycle that had acted as a reset button each autumn halted microbial activity and sealed carbon back into suspension, but it failed to complete. Dr. Katie Walter Anthony, a permafrost researcher at the University of Alaska Fairbanks, had spent years documenting methane bubbling from thermokarst lakes, shallow ponds formed when permafrost thaws and ground collapses. Her models had projected gradual, linear increases. What field teams reported in late 2024 was neither. Methane flux measurements from autonomous sensor arrays in the Yamal Peninsula showed readings 40 to 60% above projected baselines during months when emissions should have been declining. Ground-penetrating radar revealed that the active layer had deepened by an average of 32 centimeters across monitored sites in under 2 years. The process is called abrupt thaw, and it is distinct from the slow degradation that climate models have historically used. In abrupt thaw, the ground does not simply soften, it collapses. Thermokarst formation and retrogressive thaw slumps can release carbon stored at depth in decades rather than centuries. As ancient organic material is exposed to microbial activity for the first time in thousands of years, bacteria produce carbon dioxide under aerobic conditions and methane under anaerobic conditions. Methane is, over a 20-year period, approximately 80 times more potent as a greenhouse gas than carbon dioxide. The two processes do not cancel each other, they compound. Ecological disruption arrived before the headlines. Boreal forest stands in Alaska and Siberia began destabilizing as the ground beneath them lost structural integrity. Trees tilted into what locals call drunken forests, which expanded significantly across monitored zones in 2024 and 2025. Infrastructure followed. In Yakutia, Russia, approximately 70% of buildings sit on permafrost foundations. Roads buckled, and pipeline support structures required emergency reinforcement. The Russian Academy of Sciences had estimated permafrost degradation could cost Arctic infrastructure between $200 billion and $300 billion by 2050. Events from 2024 suggest that timeline may have been optimistic. Then came the systemic concern. As permafrost releases methane, it accelerates warming. As warming accelerates, more permafrost thaws. The feedback loop does not require human input to continue. Researchers have proposed interventions. In northern Siberia, a project called Pleistocene Park has tested whether reintroducing large grazing animals can compact snow in winter and lower ground temperatures by reducing the insulating snowpack. Early results showed localized temperature reductions of up to 2 degrees Celsius. Promising, but small and isolated. Other proposals: reflective coatings, refreezing technologies, and targeted methane capture, each face the same constraint. The scale of permafrost spans multiple nations, remote terrain, and depths reaching hundreds of meters. Any intervention remains orders of magnitude smaller than the system it attempts to stabilize. The permafrost preserved what the atmosphere once held. It is now returning that record to the surface faster than the systems built to monitor it were designed to process. The question is no longer whether it will continue to thaw. The data from 2024 onward has answered that. The question is whether the systems built on top of it, economic, infrastructural, and ecological, were ever designed for a world where the ground itself is in motion.